So what we have here is a part of a car. Some parts are movable, some other are fixed, and we can move the movable parts with this 3D mouse. The goal of this application is for the industry to test that a part that has been designed in CAD may be actually fitted in its location. Because with CAD you can design parts, you have their shape, their geometrical structure, but you are never sure that it is possible to actually assemble the system. So it's a virtual system to test the assembling process. There are two interesting things. It's 3D, but a lot of software are 3D now. We use a 6D mouse, it's not very important. The two main features are, first, the fact that we work on models directly derived from CAD. Here we have a model extracted from CATIA, and the model we obtain has about 300,000 polygons. So it's a big model, and it means that the algorithms that, for example, detect collisions between objects has to be sufficiently efficient to run in real time. The second main feature is the fact that the physical behavior of the object is as accurate as possible. Because if we decide with this application that this part may be assembled, it is necessary that in the real life this is also true. Otherwise the application has no use. So we manage the contact points, not only one, but in some cases several contact points. And if you have a collision with several contact points, the physics is much more difficult than if you have one contact point. And then we also manage the friction, the behavior of the object during the contact. So it's just like in the real life. If you can insert the part in its location with the virtual world, we can guarantee that it will be possible in the real world. Here we have the exhibition system, so it's not very intuitive, but we may think that what we really use for working is not a TV, but a wall with an image. Not only one image, but two images with one image projected on the floor. And then you are really inserted in the environment. You feel the objects like if they were around you. And we don't use a space mouse, a 6-dot mouse. We use a master arm, an haptic arm. We can move the object with the haptic arm and feel the feedback when we collide with the environment. So this is this application.
Very good. And the company is called CA Tech, right?
Yes, it's the French Commissariat à l'Énergie Atomique. It's the Atomic Energy Commission, the French research department on nuclear energy. But of course, this has nothing to do with. We are in a department that used technology developed for the nuclear in the past to assist industry to be more competitive.
That's all we needed. Thank you very much.
Okay, this is a project which is called PICTIC. It's a EDFR funded project from the Commission, and it's a technology platform to develop printed electronics. So printed electronics is flexible electronics. It's to make electronic devices, but by using graphical printing. So here, for example, you got photodiodes. These are photodiodes that you usually see as a little silicon chips. In this case, you got 1,000 photodiodes printed on a flexible substrate. And the idea is really to be able to make new application thanks to this electronics. And I can show you one application. This is, for example, a touchless interface. It's an interactive tablet, but you don't have to touch it to interact with it. So if I show you, for example, if I want to on-off a device. So this is one, but this PICTIC platform, the goal is really to develop this and to make the pre-industrialization to bring it from lab to fab, so to transfer it to industry. So this is the case for this device. We launch it we launched a startup with it, which is called iZorg, which is really make the industrialization of the flexible photodiode, build the product, and sell it. So, and the research platform goal is really to launch new startups and to transfer industry based on this flexible electronics globally. If it can work, I will show it to you. But it's pretty strange that everything is.
Yeah, it happens a bit.
Cameras
10
they are
years
very
ago
shy.
it used to work. And this technology.
Temperature sensor, pressure sensor, lots of large area sensing. So, for example, you can measure the pressure in a bed. So when you have a people in an hospital, sometimes you got trouble because you don't move in your bed. So you can measure the pressure and see if the people is this kind of applications. And when the light is full, you see it like this, and you see the interaction with my hand. I don't touch the surface, but I can interact with it. This is really the logic. Then, what do you do with this? This is not an application. For example, you can make some object recognition. For example, you want to know there is an object on a surface. Is hesitating. Which one is it? Who is going to win? The T wins. It is right. Okay, so
and it doesn't matter what side it
this
be,
is
right?
Normally not.
Amazing.
You can make some mistakes sometimes, but globally no. And so this is used in logistics for smart shelves, for example, to know how many objects are on a shelf and if you have to refill it.
Great.
Then other application is really touchless interface, so you can turn it off. For example, if your hands are dirty, you can interact with something. If you are in a surgical environment, you cannot touch your screen, then you can still interact with it. So this is touchless interface is very interesting for that. But then you can also have a 3D interaction. You can also have the level. It's not only where a position, it's also an action, okay?
The volume, right? I see.
So a lot of application can be done thanks to this interface. And so this is really discussion with people to, this is also gaming, for example. So you can play without touching the thing, you can make games. I'm not good, I'm really not good. Game over. Okay, so you can play without. It's really a new interface.
It's great.
Okay.
Thank you.
Oh well, this is a setup that demonstrates the trapping and cooling of atoms. So, as you can see on the screen here, we have. This is a live feed from this camera that looks inside a vacuum chamber, and as you can see, there's a small dot in the center, a glowing dot, which is actually several millions of atoms that are being trapped and suspended inside, and it's currently at a temperature just above absolute zero. So that means the atoms there are almost standing still. They're hardly moving at all anymore.
And what is the force that's keeping them in one place?
The technique behind it is called magneto-optical trap. So we use coils that produce a certain magnetic field, together with 6 laser beams from all directions to cool and trap the atoms in a certain region in the magnetic inside this vacuum chamber. So this is the technique itself has been around for almost 2 decades. I mean, there was a Nobel Prize on this discovery or showing that it's possible to do this, to cool atoms this way. But this has so far been almost entirely been in research laboratories. So you had large setups which are huge, require big lasers. And currently the development of lasers and electronics is in a state where we can actually bring this outside, make it more compact. And one of the advantages is also that we could even if you design this carefully enough, you can actually run the entire setup on batteries, so that it gives an opportunity to actually bring the entire setup outside and do interesting experiments. Like one of which we're doing in the iScience project, which is an FP7 project with many collaborators in Birmingham, Hamburg, Hanover, University of Nottingham, lots of research institutes that are collaborating to build a mobile atom, cold atom-based gravimeter. So that is, it might look similar like this, but it's more compact, and it can measure basically the gravitational acceleration. So, if you have these cold atoms, the advantage is they are also very sensitive to disturbances, for instance, gravitational attraction. So the idea then is, if you could use this technique to make a mobile gravimeter, you can map out areas to see how gravity is changing, and this is usually an indication there's disturbances or changes in underneath the surface due to pipes, infrastructure, or maybe some oil or gas wells, or other stuff that you want to explore and see what's underneath there. So that's one of the that's one of the current applications we're trying to.
So this was made in Birmingham, in University of Birmingham, right?
Yeah, that's true. This setup is just a demonstrator. So the actual setup, that is being assembled in Birmingham. Different parts are built in other research institutions, but the entire setup is tested and assembled in Birmingham. So that's unfortunately we can't bring the actual setup here because the project is still running, and there was danger on that there could be mishaps in the transportation that we wouldn't like to risk. So that's why we built a separate thing in about 2 months' time. We had to assemble this from parts we have, and we were very surprised and very happy that we could actually get it to run here in outside of a laboratory. So, yeah.